Let's start on this circle at about this point right here. There are a couple of different ways we can talk about the motion of this point. We might want to call it a particle. It sort of depends on the context. But one way we can talk about the motion of this point, if it's going around the circle like this, is that it's making a linear motion around the circle. And I know I mentioned this before, but I'll just say it again here. This is not a line in the strict sense of the word. A line would be a straight line, but it's a two-dimensional object, right? It's two-dimensional motion. It's going around this, it's walking on this path. It's like walking on a path. And the other way, or another way that you could talk about this motion is to talk about it as though you were standing on this point right here and watching the particle move along. I'll go ahead and put its endpoint in here at the end. If you did that, you'd be starting facing in this direction, but you'd end up facing in this direction. So there are two different kinds of motion going on here. The motion of the particle itself, which is linear, and the motion that you take as you watch the particle move, which is what we call angular motion. And we can also talk about linear and angular speed. If I watch this particle move and it moves like this, I would say it has a slow linear speed. As I stand in the middle of the circle and watch it move around, I have a slow angular speed. If the particle moves much more quickly, then its linear speed is faster, and my angular speed watching it is also faster. We have a formula from geometry or algebra for linear speed. It's distance equals rate times time. We're going to change this up a little bit in this class, though, because our linear distance is not a straight line. It's this curve that we've been calling S. So I'm literally going to erase the D for distance, and replace it with S. I'm also going to replace R for rate with V for velocity. We'll get into this a little bit more in calculus, but velocity is a rate of change of position. It's a rate. Velocity is a rate. So I can use the R or I can use the V. And so for consistency with your textbook and for practicality and consistency in the convention used in trigonometry, I'm using the letter V to stand for velocity. So now if I know how fast a particle is moving and how long it's moving for, I can tell you how far it's gone. This is really just a special case of distance equals rate times time. Oftentimes, though, I'm looking for the speed, so I need to solve this for v for velocity. I'm going to solve this for v by dividing both sides by t, and I get velocity equals s over t. I actually don't have this formula memorized. I have this one memorized. Distance equals rate times time with a couple of adjustments for the context I'm working in. Your textbook has this one written down as the one to be memorized, but it's up to you. We can also write the formula distance equals rate times time for angular speed. How fast am I turning if I'm standing in this position, looking here and following along as the particle moves along the outside of the circle. But this time, the distance is measured in radians. It's how far I turn. That's a measure of distance. So I'm going to erase distance and replace it with theta. The number of radians I turn is my distance. The thing I'm going to use for rate in this case is the Greek letter omega. It looks like a funny W. And I'm not sure why omega, that's the lowercase omega. I'm not sure why omega is the letter that's used here to indicate angular speed or angular velocity, but that's what they use. Once again, I'm usually looking for the speed, so I'm going to solve this for omega. If I divide both sides by t, I get omega equals theta over t. Once again, your textbook has this version of the formula memorized, but really this is just a version or sort of an adjustment to the distance equals rate times time formula. So whichever one works for you. If I were making a note card, I would probably include these two, or I might even just write down d equals RT, and know that I have to adjust it in one special way to get this formula and in a different special way to get this one. If you prefer, of course, you can write these on a note card and use them instead. Keep in mind that sometimes what we're looking for is S, in which case for this one I'd have to multiply both sides by T. Or maybe what I'm looking for is T, in which case I'd have to multiply both sides by T and divide by omega. So just having this version instead of this one isn't necessarily going to be the be-all, end-all anyway. So I like these ones because they're quite simple, and then I can adjust them as I need. Let's take a look at an example. Let's say we have the wheel in a car. Maybe I'll make it a cart. I think it's a little easier to draw. And let's say that we know that the radius is 24 inches or 2 feet. Now, let's say that there's a bug right on the rim of the wheel. How fast is the bug moving in terms of linear speed and in terms of angular speed? In order to determine that, we need to know how fast the wheel is going around. And oftentimes the way that's given, or the way that information is given, is in revolutions or rotations per minute. In this case, I'm going to say that the wheel is going around 20 times every minute. And you could convert that if you wanted to. 20 revolutions, it's a V, per minute is equal to 20 revolutions per 60 seconds. And that's 1 revolution every 3 seconds, or 1/3 of a revolution per second. So it kind of depends on what the context is and how you want to set the problem up. I think in this case, since we don't really have a context outside the size of the wheel, and we don't really know what kind of cart it is or whether it's going to be traveling for 20 minutes or several days, so I think I'll just stick with my original units, revolutions per minute, so I can get rid of all of this. And then the question we are trying to answer is, what is the linear speed of the bug? How fast is it traveling around the circle that is the wheel? And also, what is the angular speed of the bug? How fast is another bug? Let me put another bug on the wheel. This is kind of fun, talking about bugs. How fast is the bug here spinning if this bug is always facing in the direction of this bug? That's angular speed. We want to answer both of those questions. So let's answer the linear question first. We've been asked for the linear speed of the bug, so we want to use the formula that's written speed equals, or velocity equals S over t. Remember, in this case, S stands for the arc length, not the speed. Speed is velocity. And I don't know my velocity, that's what I'm looking for. But I do know something about my arc length. I know that S is the distance the blue bug travels around the edge of the wheel, around the circle. Well, it's going around 20 times every minute. So it's going to go around 20 times 2 pi r, the circumference of the wheel, every minute. And that's where t comes into play. T is 1 minute. T is time. Now all I have to do is replace r with the radius I was given. My pen is acting up for some reason. Let's try that again. Replace r with the radius I was given and tidy this up a little bit. I get 20 times 2 pi is 40 pi, times r, which I was told is 24 inches, per 1 minute. 40 times 24 is 80, plus 16 is 96 pi inches per minute. And what I'm looking at here is inches per minute. This is a I want to use a white highlighter here. This is a rate, inches per minute. The fact that there's a pi in it just comes from the fact that there's a pi in the computation of the circumference, right? If a revolution is, one revolution is the circumference of the circle, then the circumference of the circle, the revolution, is going to have a pi in it. It's 2 pi times the radius, 2 pi times r. So my circumference is going to have a 2 pi in it, which means my answer is very likely to have a pi in it. This is the exact value, 96 pi inches per minute, the exact value of the answer for the linear speed of the blue bug. Now let's go find out what the angular speed is. We have a formula for that as well. It's omega, that's the angular speed, is equal to theta over t. So my time, again, is 1 minute. And theta is the angle that the green bug will travel through as it watches the blue bug go around. So it's going to stare in this direction and then this direction, and this is, it's going to go around the circle facing the blue bug at all times. So it's going to go through multiples of 2 pi, right? And we're told that in each minute, the wheel goes around 20 times. So we have the green bug turning 20 times 2 pi, one full circle. And that's 40 pi radians per minute. So this is the answer to what is the angular speed of the bug. This was the answer to what is the linear speed. So as you can see, these two are very different answers. First of all, this one's in radians, and this radians per minute, and this one's in inches per minute. But also notice that there's a similarity. It's almost a shortcut. This numerator was 20 times 2 pi, and this one was 20 times 2 pi times r. That's the only difference. That's kind of a shortcut. If you want angular velocity or angular speed, you take how many revolutions per time unit, in this case it was per minute, and you multiply it by 2 pi. That gives you angular speed. If you want linear speed, take that same computation, the number of revolutions per time unit, and multiply it by 2 pi, but then also multiply it by r. And that's the only difference. But now you know why, and you know where those come from. There's one other quite interesting thing we can do with these formulas, but I think I'll do that on the next screen. So now here's another interesting question. What if you know the linear speed and you want to convert that to angular speed? Well, it turns out that there is a relationship between linear and angular speed, and there are a couple of ways to determine what that is. One would be to take this formula here and solve it for v. That gives me v equals s over t. We did this on the previous screen, and I said you don't need to have this memorized. You can just memorize this version or have this version on your note card. Well, if I want to change it, I can just change it. I just use a little bit of algebra. But now, if I take this and look at it from another angle, no pun intended, I know that s is arc length, right? And I have another formula for arc length. It was s equals r theta. So what if I replace my s with r theta? And then I can think about this as r times theta over t. And this formula, when I solve it for omega, gives me omega equals theta over t. So I can replace this with omega. That gives me r times omega. In other words, v is equal to r times omega. The relationship between linear velocity, which is v, and angular velocity, which is omega, is that v is equal to r times omega. Well, that's exactly what we found on the previous screen. If you know the angular velocity, all you have to do is multiply it by r to get the linear velocity. There's kind of another way to do this, and it's a little less elegant, but I think it makes a little bit more sense algebraically. And that is to say that if I solve my first equation for t, I get T equals S over V. If I solve the second equation for T, I get T equals theta over omega. Now, if these are both true, and T is the same in both cases, then those T's must be equal to each other. In other words, S over V must be equal to theta over omega. If I make the same substitution as I did before for S equals R theta, I get this equation. And if I divide both sides by R, I get theta over V equals theta over R times omega. If these two fractions are equal, and the numerators are already the same, then the denominators must also be equal. So V has to equal R times omega. And that's exactly the same result as I got over here. I kind of cheated. I feel like this is less elegant, but I still got there, and I used legitimate algebra to do it, so no harm done. Okay, a quick example here. Let's say that a truck is traveling at 45 miles per hour. What is the angular speed of the wheel if it has a 16-inch radius? If you imagine a wheel has a pebble in it, and it's moving along in this direction, it's going to leave a tire track. And every so often, as that pebble hits the ground, it's going to leave a pebble mark, some kind of a marker, right? And that is the same as one circumference as the tire, right? That's one circumference. And so when we say that the thing is going 45 miles, we mean that the tire is going around so that it leaves a track 45 miles long. And figuring out what 45 miles is just a certain number of circumferences. That's one of the reasons we can talk about the circumference or an arc of the circumference as being a linear measurement, because it leaves a linear measurement. So here's our linear measurement. Our linear speed is 45 miles per hour. That's my V, 45. And I'll go ahead and write it as miles per hour. And I know that that's equal to radius times omega. Well, radius was 16 inches, and omega is what I'm looking for, the angular measurement. So, the angular speed, rather. So to get omega by itself, I need to divide both sides by 16 inches. I get omega equals 45 miles divided by 16 inches times 1 hour. Ultimately, this is going to be a measurement of either miles per hour or inches per hour. Now, omega is usually measured in inches or meters or centimeters per second, but we're just doing an example here, so I'm not going to sweat the small stuff. Let's just convert this into, I could take 16 inches and convert it into a small amount of 1 mile, or I could take miles and convert it into inches. I think I'll do that. 1 mile is equal to 5,280 feet. For some weird reason, that's just something I have memorized. But you can always look it up. And that's 5,280. 1 foot is 12 inches. So that gives me 63,360 inches in a mile. So wherever I see a mile, I can replace it with this many inches. So I'm going to do that right here. I'm going to rewrite this as omega equals 45 times 63,360 inches, I'll write it as IN, over 16 inches times 1 hour. Now the inches cancel, and the rest of this arithmetic gives me 178,200 per hour. I'm running out of room. It's just so typical of me. I can move these over a little bit more. There we go. Okay, so 178,200 per hour. My inches are gone, right? I have no length measurements left. I'll come back to that in just a minute. So whatever I have this many per hour. Now, what was I doing? What was I looking for? I was looking for the angular speed. And since I've done everything in terms of, well, it doesn't really show here actually, but I've done everything in terms of radians. So, and that's because of my formulas, right? My formulas have theta in them and they were all derived using radians. So I have to use radians here. So I have 178,200 radians per hour. And that's my angular speed. So this is my answer to the question that I asked up here. The truck going 45 miles an hour, what's the angular speed of a wheel with a 16-inch radius? Now, one last thing I'd like to talk about in this video, and it's kind of related and kind of not. It's related in that it's related to everything that we do in trigonometry. Radians are what we call unitless measure. And what I mean by that is that, for example, down here at the end of this problem, when I got rid of my inches and I was just left with some number of something per hour, that some number of something was radians. There's no unit involved, but it had to do with the linear speed, the conversion of feet to inches, all that linear conversion that we did. It was that many, this omega was that many things per hour. But omega is always measured in radians per time. So we don't have a radian. I put one in here, but we don't have a radians in here. But if there's no unit at all in a case like this, then we know that unit is radians, right? Something else I did earlier, let's see, I had 180 degrees was equal to pi, and I think I said radians at that point, but I don't need to use the label radians. So I could say 180 degrees divided by pi is equal to 1. I don't need the label radians down here. Radians, pi down here is in radians, but radians are a unitless measure. So something to be careful about is that if I give you an angle and I ask you to convert it, or if I give you a problem with an angle in it, let's say theta, I want to put it somewhere where you'll see it, but I don't really want it to conflict with the other stuff that I've got here. So I'll put it in its own little bubble. This is unrelated to anything else, not directly anyway, to anything else on the screen. If I say theta is equal to 265 degrees, then you know it's degrees. But if I just say theta is 265, then that's 265 radians. There's no label there at all, so you assume that it's in radians. If I want it to be, if I want you to know that it's in degrees, I have to give you the degree symbol or the word degrees, right? I must include either the symbol or the word degrees. If you don't see it there, you must assume that the unit we're talking about here is radians, because radians are a unitless measure. Well, that's pretty much it then for this section. We've spent a lot of time talking about circular things, considering that we're actually starting with the trigonometry of right triangles. It's kind of a funny place to start, but that's how the textbook lays things out to get us going, and that's fine. In our next section, we're going to be talking about trigonometry of right triangles specifically. So far, we haven't actually done any trigonometry. We've talked about how You can measure angles in either degrees or radians, but that doesn't have anything to do with trigonometry. As we go into the next section and as we proceed through the course, you will see angles measured sometimes in degrees and sometimes in radians, and you'll have to use those within the context of trigonometry. So up to this point, we haven't done any trigonometry yet, but what we have learned, we're going to be using as we go through and study trigonometry for the rest of the quarter.